All right, let's get right into it. For the past few years, we've all been watching this absolute explosion in AI. It feels like magic, right? But what if I told you the secret recipe wasn't magic at all? Turns out it's something way simpler, and it was kind of hiding in plain sight the whole time.
I mean, this is the question, isn't it? One minute, AI is this kind of niche thing for researchers, and the next it's writing code, it's making unbelievable art, and it's shaking up entire industries. So, how did we get here? What was the switch that got flipped to unleash all this power?
You see, for the longest time, making AI better felt more like an art than a science, kind of like digital alchemy. The common thinking was that progress came from these brilliant, clever new designs or stumbling upon some unique, one-of-a-kind magic architecture. It was unpredictable, it was messy, and honestly, pretty frustrating for the people in the field.
And then, in 2020, everything changed. A team of researchers at OpenAI published a paper called Scaling Laws for Neural Language Models, and it just dropped a bombshell on the entire community. They found that the secret to incredibly powerful AI wasn't some complex new trick. Nope, it was a simple, predictable, and, well, scalable recipe.
So, to really appreciate just how huge this was, we gotta go back and understand the puzzle everyone was trying to solve. What did the smartest people in the room think was the key to building better AI before this paper came along?
Well, the focus was almost entirely on the tiny, intricate details of the model's design. Should we make it deeper, with more layers, or maybe wider? Which little settings, the hyperparameters, would finally unlock its potential? The whole thing felt like this high-stakes guessing game, this endless search for a perfect blueprint that no one could quite pin down.
So the OpenAI team decided to do something different. They decided to stop guessing and start measuring. They basically said, let's stop approaching this like artists and start acting like physicists. They set up this massive, methodical experiment to find the fundamental laws that actually govern AI performance.
And when I say massive, I really mean it. We're talking hundreds of different models, ranging from tiny to, at the time, gigantic. They fed them enormous, varied data sets. They measured everything, meticulously tracking what was going on to separate the variables that truly mattered from all the noise.
So after all that painstaking work, what did they find? Well, what they found was revolutionary because of how simple it was. Performance wasn't about some clever, bespoke design. It was overwhelmingly about just three simple factors, and they all boiled down to one thing: scale.
Okay, so factor number one is model size, which the paper calls N. The easiest way to think about parameters is like tunable knobs on a giant machine. The more knobs an AI has, the more finely it can tune itself to learn complex patterns in the data, and the researchers were smart. They focused only on the core processing parameters, the real brain of the model, to get to the true source of its intelligence.
Factor number two, data size, or D. This one's pretty straightforward. It's just the total amount of information, in this case text, that you feed the model while it's learning. The more high-quality stuff it sees, the more it has to learn from. Simple as that.
And finally, factor number 3 is compute, or C. This is just the raw horsepower you throw at the problem. And we are talking about just mind-boggling amounts of processing power, measured in units like petaflop days. To give you an idea, a single petaflop is 1,000 trillion calculations per second. It's an insane amount of energy.
And here's the beautiful, elegant discovery they made. As you increase any of these three things, the model size, the dataset size, or the compute, the model's performance gets better in this incredibly smooth, predictable curve. It's not random. It's not a lottery. It follows a mathematical power law. And for the best results, you have to scale all three of them up together.
And this was the real bombshell. All that time, all that energy researchers spent agonizing over whether a model should be super deep or super wide, the paper found that it barely mattered. Seriously. As long as the shape was reasonable, it was way, way less important than its overall size. This one finding just busted years and years of conventional wisdom.
So this discovery wasn't just some interesting footnote for a research paper. It completely changed the game. It literally wrote the new rulebook for how to train state-of-the-art AI.
Which brings us to the big, strategic question that every single AI lab has to face. You've only got so much money to spend on these incredibly expensive computer chips and the electricity to run them. So where do you put your chips, so to speak? Do you make the model bigger, feed it more data, or just train it for longer? And the answer the paper gave was completely counterintuitive at the time. The scaling laws predicted that to get the most bang for your buck,
You should spend the vast majority of your compute budget on one thing, making the model bigger. Just increase the number of those parameters. Everything else was secondary.
I mean, just let that sink in for a second. The new best-in-class recipe was to build a ridiculously gigantic model, show it a surprisingly small amount of data, and then stop the training process way earlier than anyone thought was right. The takeaway was wild. Don't train a small model to perfection. It's much better to train a huge model imperfectly.
And the reason this crazy-sounding strategy works is a concept called sample efficiency. What the paper proved is that larger models are just plain smarter learners. They're quicker on the uptake. They can reach the same level of performance with way fewer examples than a smaller model needs. They don't just know more, they actually learn faster.
So as you can imagine, the publication of these scaling laws didn't just make a few waves in the research world. It kicked off a revolution that led directly to the AI-powered world we're all living in today.
Right after this paper came out, you started seeing models like GPT-3 with over 175 times billion parameters. These weren't just a shot in the dark. They were a direct consequence of the scaling laws. Companies built them based on the confident mathematical prediction that if they made the model astronomically bigger, they'd get a predictable astronomical jump in its abilities.
You can literally draw a straight line. The paper gave everyone the blueprint. That blueprint gave companies the confidence to pour billions of dollars into scaling up their compute and their model sizes, and that investment, well, that directly led to the explosion of powerful AI tools that are now everywhere you look. When you boil it all down, the scaling laws gave us a reliable roadmap. They transformed AI development from this mysterious art, full of hunches and guesswork, into a predictable engineering discipline. For the first time, you knew that if you put more scale in, you were guaranteed to get more performance out. And yet the researchers themselves end their own paper with this really provocative thought. These perfect power laws, they can't go on forever, right? So as we start building models with not just billions but trillions of parameters, what happens next? Do the laws just break? Do we hit a hard wall? Or does something else, something entirely new and unexpected begin to emerge? And that right there is the next great puzzle for AI.